thank you. It's wonderful to have in-person conferences again. And it's a privilege to actually organize this with Ashwini, though I must admit the bulk of the work was done by Ashwini. My job was relegated to only sending emails, and I mixed up things quite a bit. Anyways, so again, it's a great pleasure to chair this session. The first speaker is Professor Arun Yethiraj from the University of Wisconsin-Madison. He's a VW Bascom, did I pronounce it right? Melok Bascom Professor of Chemistry. He has made immense contributions to soft condensed matter systems from the theoretical perspective in development as well as applications. Till very recently, he was a senior editor of the Journal of Physical Chemistry. Currently, he is visiting IIT Bombay as a distinguished professor, and just another feather in his cap, he is awarded the Theoretical Chemistry Award in the autumn ACS meeting. So with that, I'll keep it brief so that Professor Yethiraj can actually enlighten us with his talk. Arun.
Great, thank you. Thank you. I'd like to thank everyone for being here, and also the Nilanjana for letting me invite myself to ICER, which is what actually happened, because I was coming to India and uh, I wrote to her saying, "Hey, can I visit you?" And she said, "Yes, of course." So it's a pleasure to be here. It's my first international trip in a couple of years, and it's been a great experience so far. I'm looking forward to the conference today, and congratulations to Saurabh on his big move. So I'm going to talk today about machine learning, and this is, if you'd asked me about machine learning 2 years ago, I would have had a very much negative opinion of the field, okay? Because I used to joke that in my group we do human learning, not machine learning. And what happened was one of my students, decided to work in this field without my knowledge, and then his results were so good that we started, really getting intrigued by the power of what you can achieve by looking at computer simulations through machine learning. Okay, so the problems, if you think about. Okay. Okay, now it works. I think it had gone to sleep. So if you think about physical systems, in statistical mechanics, we talk about phases in the Ehrenfest sense. So this is a very old way of thinking about what a phase is and what a phase transition is. But if you look at physical systems, and here's one which is very, very popular: liquid-liquid phase separations in cells, where they take a cell and they notice that there are these liquid regions or droplets. And what you see in these droplets are a sort of a concentration of certain proteins and RNA. One of the things people think is that this might have been responsible for the origin of life, because you can have these droplets without membranes. So you have compartments without membranes. And so the question is that really a phase? Is that a phase in the Ehrenfest sense? But does it matter if it is or not? It's just another sort of structure that we see in a real system. And does it matter if we classify it as a phase or not? So this turns out to be important for the things I'll be talking about, because machine learning doesn't actually do anything about thermodynamics. So we predict and phase transitions without ever thinking about the thermodynamics, but only the structure. And in this system, for example, polymer coacervates is another one, where you mix a polyanion and a polycation and you make two different phases, where most of the experiments just see, dense regions or structures. And the question is, does that constitute a phase? Or if you looked at these coacervates, not with homopolymers, but with diblocks or triblocks, they make mesophases or microphases, some people call them, of different structures, gyroids, Frank Casper phases. And the question is, the structure is more important than the thermodynamics, because that's what is measured. Okay, so that's a sort of a brief introduction to this idea that when you're thinking about phases, you might actually be more interested in the structures that are formed rather than the thermodynamics of your system. At least that's what is measured. But we got interested in this system, which is ionic liquid. So if you take sodium chloride, it is solid, of course, at room temperature, crystalline, but something like an ionic room temperature ionic liquid is liquid. And there's no solvent. It's just, in this case, it's NTF2 and BMM. It's just anion and cation, but they don't pack very well, so they're liquid, they're not solid. And they may have many applications. So in fuel cells, they have very high conductivity, very high, low vapor pressure. So they're, as a working fluid for reactions, for conduction, they're very promising. And one of the ways of, but of course they're liquids, so you can't make a device out of a liquid. And one of the ways of doing that is to encapsulate them inside a membrane. So suppose you were to make a polymer, like a diblock or a triblock, that would be the pink region. So you make a polymer with a gyroid phase, and then if you were able to put the ionic liquid inside, then you would have a membrane that had an ionic liquid as the working fluid. Or if you wanted it in directional, then you made a single crystal of these phases, which are hexagonally packed cylinders. You could have the ionic liquid inside that. So this is an idea from Tim Lodge many years ago, where he said, well, you can't actually push these ions into this small channels because the viscosity is very high. So can we sort of get the ions dissolving the polymer at some temperature and then phase separate it? And then when they're phase separated, you have this membrane, and you cross-link the polymer, and then you have this membrane with the ionic liquid inside. So that was the idea. And what he did was he looked at the phase behavior, in this case of PEO and EMIM BF4. So BF4 is, of course, just BF4, but EMIM is this imidazolium ring, and if you have 4 carbon atoms, it's BMIM, butyl. If you have 2, it's EMIM, ethyl. So the things he found were kind of interesting. So first of all, it has an LCSD, so it phase separates upon cooling. So the system phase separates upon cooling. This is not unusual in polymers. It's not well understood. That people argue about it. And the other thing that was interesting was that this critical point was at a very high weight fraction. Usually it's at a very low weight fraction in polymers. So that was interesting. There's very weak molecular weight dependence. So I thought of this and thought that this might be a way of understanding the LCSD, in addition to providing insight into the physics of his particular system. And then he published this other paper where he looked at a very, very small change. So he took EMIM and added a methyl group right at this acidic carbon. And so that's a very small change. You don't expect this to change the thermodynamics very much. But what he found was that this phase diagram changed quite dramatically when he made that small change. Okay, so it was much different. This is the critical point has shifted from there to here, and then the temperature has changed by about 50 degrees Celsius. Okay, so this is a big change from a very small change in the chemistry. So this is interesting. So this is so we thought that this might be a way of this might be a really good system. So it turns out that this is a really interesting problem. It also turns out to be the hardest problem I've ever worked on. It took many, many years to get going on this. And we had to start from scratch. And in the sense that when we took the standard, we do molecular dynamics for the most part and statistical mechanics. And the standard force fields that you would use, OPLS or CHARM, they did not predict, one of them did not predict a phase transition at all, and the other one predicted a phase transition at all temperatures that we looked at. Okay, so it is a very, very subtle problem. And what we had to do was develop force fields from quantum calculations. So one of J.R. Schmidt is a colleague of mine, and one of his students, Jesse McDaniel, was at his, not his thesis defense, but we have this mentor committee meeting at fourth year. And so he was looking at imidazolate and CO2 interactions, and they had this way of using sort of a gas phase uh, dimer energy calculations with DFT, and then fitting it to symmetry adapted perturbation theory for the different components. So you have electrostatic dispersion. uh, this is the delta Hartree Fock, the induction, exchange, and you can see that the different components are very different in magnitude, but they add up to give something. This orange is the SAT, which is in really good agreement with higher level, very high level quantum calculation. So this is a way of getting a force field that is quite accurate. Here's the proof, is that you take the MD with this. This is a fully polarizable. All the atoms are polarizable. It's a very expensive force field, and you can compare to experiment, and they're all in very good agreement for a number of different static and dynamic properties. So this is a good force field, a great force field, no adjustable parameters. So if it doesn't work, you're kind of stuck. There's nothing you can change. Okay? You get what you get, but it's accurate for the system. And so what we did was we took that force field. So here it is with all the heavy atoms, and these orange things are Drude particles. They're massless charged particles that change the polarization of that atom, and then the white ones are hydrogen. And we went through a hierarchical sort of coarse graining to knock off either the polarizable particles or the hydrogen, and we came up with this sort of force field where you have a united atom for each of these heavy atoms. You have to keep the anion atomistic, and this all of these are adjusted to reproduce the properties of the real thing that we believe in, the quantum force field. Okay, so we've got a force field for this ionic liquid. We did the same thing for the polymer, and we had two immediate surprises. One was that for PEO, which is probably one of the simplest polymers in ionic liquid, the equilibration times are of the order of microseconds. So you have to do very, very long simulations to get the properties of this polymer. These are three different trajectories. That's the radius of gyration, the size as a function of time. And the distribution is sort of roughly similar. And we average these three things to get the properties. And then if you look at the scaling of the size with the molecular weight, we get something that agrees. You want to look at this exponent, 0.56, agrees with experiment, really well. So it works not only for the ionic liquid, but as for the polymer as well. So there was a big controversy. Some people thought this exponent should be 1. There were experiments that said this should be rod-like, and so this was something that was good. Okay, so now we want the phase diagram. So, and that's actually the heart of my talk, is how do you get the phase diagram? In principle, if you want to get the phase diagram of a system in using simulations, this is how you would do it. The standard way is called the Gibbs ensemble. So you need three things to be satisfied. You need the chemical potential of each species, the temperature, and the pressure to be the same in the two coexisting phases. So what you do is you have two boxes, and you move the particles in each box, and you do that with the Metropolis algorithm. You do it so that the temperature is constant. Okay? So you choose the acceptance of a move so that temperature is constant. Then you have to do a volume change where you decrease the volume of one box and increase the volume of the second so that the total volume is fixed. And then you accept that move in a way that the pressures are constant. So there's a certain change in the energy due to decreasing it and to increasing it, and you accept, your acceptance criterion is adjusted so that guarantees the pressures are equal, and then you exchange particles between the two boxes. So take this one out and put it there, take, and the red one, and that you adjust your acceptance criterion to satisfy the chemical potentials being equal. And then if you do that, then for this binary mixture, as a function of time, one of the boxes goes to one concentration, the other box goes to another one, and those two concentrations are your coexistence concentrations. So this is how you would do it, or you used to do it, and it works quite well for many systems, and it completely fails for our system, because not only can't you insert the polymer, right, from one box to another, it's a big object, the ionic liquid itself is hard, because these are a dense liquid, it's hard to insert anything. And besides, you have to insert an ion pair, because your system has to be electrically neutral. So you have to insert both the cation and the anion at the same time. And so that was the challenge. And we uh, were kind of stuck on this until one of the things that my student did was to say, well, this was my idea, but I said, why don't we just take a very long box and then allow it to phase separate in the box, and then this will give us, a concentration profile, and then we can extract the two coexisting concentrations from that concentration profile. So that's how we were going to do it. Except what happens is that this interface, it moves during the course of the simulation. Okay? And so if you just took the average concentration, it turns out to be constant. You really can't measure it that way. So what he came up with, this was Hyante. So it's a different system, but we have a blue and a red species, and this is a Monte Carlo simulation. So as a function of the coordinate, we have the concentration profile as a function of, let's say, it's sort of like time. Okay? And you can see that this interface moves quite a lot. And so if you take an average, you don't get anything interesting. So what he did was he came up with this convolution method where you use a concentration autocorrelation function to determine the center of the blue region. Okay? And once you do that, you say, okay, that's 0. So here's the center of the blue region is 0. And you do that for each snapshot. And then you can align all these profiles to get something that you can use to get the concentration profile. Okay, so that's what he did. It's something he picked up from when in his days as an electrical engineer. And so it works, but it only works. So there are two systems, a Witten-Rolandson mixture and a symmetric polymer blend. These are our canonical test systems. This is a polymeric system, so it's hard to equilibrate. This is a completely entropic system, so the phase transition is very subtle, so it's a very difficult system to get right. And it works compared to previous methods, far from the critical point, but you really can't get anywhere close to the critical point. Okay? So the reason is that the interface just breaks up. It just breaks up, and there is a theory that shows that the interface actually grows with the size of your box. So you can't do this by making your box bigger. Okay, so that's where we decided we had to do something different to try to get to the critical point. And what he came up with was this convolutional neural net, CNN, way of determining the phase behavior. This had been used before for two-dimensional Ising systems, and he applied it to our system. So the first step is we have off-lattice coordinates. So he had a way of using a majority rule to replace or assign each of these concentrations to a lattice point. So you have a grid interpolation method to get the off-lattice system onto a lattice. And then we use a filter with this, a filter, we optimize the filter size. And basically, you go over this lattice, and you replace each lattice point with the value of the filter. So this is not new. This is how, and then you flatten this to get a fully connected layer, and then this has a neural net that then assigns it to be either mixed or phase separated. This is not new. This is a classification algorithm. It's used most popularly to determine whether uh, you have a cat or a dog. So uh, you train this algorithm on images. It's an image classification algorithm. So you train it on the image of many, many dogs and many, many cats. And then if you give it a new image, it tells you the probability that your image is a dog or a cat. Okay? So I've been meaning to do this on people, So train it on cats and dogs, and then put people in there and see whether they're cats or dogs. Okay, so this is a danger of this method, because you know that the person is neither a cat or a dog, but it will classify them into either one or the other. Okay, uh, so that's one of the hidden dangers of machine learning, because you will get an answer, and so then it's up to you to determine whether that answer is meaningful. Okay, but uh, so we train it. We have the fully mixed. So in that interface system, we can get the mixed, of course, always, but we can also get the phase separated system sufficiently far from the critical point. So we have our two uh, training levels, and then we can use that. So you have a training set which is both mixed, and another training set which is phase separated. And then for any other system in between, you evaluate it as to whether it's mixed or phase separate, and you get a probability. So you have many, many configurations of each of these, okay, including this one. So for each snapshot, the net will tell you whether it's phase separated or not. Okay? And then you run it through the whole ensemble of snapshots that you have, and it'll give you a probability that it's phase separated. Okay, so there are many little things. For example, the algorithm does not distinguish between this and this, although we can just look at it and tell that they're different. So if you are going to use this algorithm, you have to use all rotations of your box. That's one of them. And the second thing is that the actual morphology of the phase separated system has to be significantly different from that of your mixed system. Okay, so there are some little things that are all in the paper. They're all, all these problems are listed in the paper, and I don't have the time to go and talk. But so you get a probability that it's phase separated, and then, when it's 0.5, we say that it is the critical point, or the phase separated point. Uh, as you increase the system size, this is for the Widom-Rowlandson mixture, which phase separates when you increase the density. This probability as a function of the autoparameter as a function of this state variable, in this case the density. For other systems, it's the temperature. It becomes steeper and steeper, and they all cross at 0.5. So that's just an empirical observation. So it seems reasonable to use 0.5 as your critical point, or your phase transition point, and you get really good results for the phase diag. This is the Widom-Rowlandson mixture. As you increase density, it phase separates. This is the polymer blend. As you decrease temperature, it phase separates. And where other methods are available, it is really accurate. But we have no problem going to the critical point, because we don't have to wait until it's fully equilibrated. We just need the structures. And we are training it at points down here which are well equilibrated, right? Because we have these phase separated systems. So this is an advantage, no critical slowing down. And there are some really strange things. For example, we get the critical exponents correctly. So if someone is interested in that, I can talk to you about it later. Okay, so, but this system, this method, I think it's a good method, but it doesn't really work for our polymer in ionic liquid system. Okay? So it's just too computationally intensive. You need too many configurations independent configurations, both for training as well as for evaluation. And if each independent configuration is going to be a microsecond, that is just, and you need 1,000 of them, then this is, at least not yet. It's not yet a method that we can use for such a system. So he went to this other approach where instead of using configurations, he just used the mixing, excess volume of mixing, the cohesive energy density, and the coordination number for systems with low contacts between polymer and cation, and coordination number with high contacts. So these are the independent variables he chose, and then he used a neural net to to predict the phase separated, and again he trained it on the phase separated and the mixed states, and he used that to train the system and then to evaluate it. Now the interesting thing about machine learning is that the learning curve, the human learning curve, is very, very shallow. So you can do these calculations within a day of wanting to do them. Okay, so the machine learning part, everything I talked about in scikit-learn, there are Python, this is done with PyTorch, there are Python libraries that do all of these things automatically. So it's the coding that you need to learn to do this is really, really, the barrier is really small. So that makes it a very good thing for undergraduate students. I had a high school student working with me on this as well. And I'm trying to get my son to do something because, it's like, it's time for him to be part of the family business, right? So, so here's for example, there's not much difference between these two when we look at in this case, the volume change of mixing, and similarly for the cohesive energy density. And so what we predict is that there's not much of a difference in the phase behavior. So that thing that looked like that, we don't see that at all. And so this is a sort of prediction that, yes, your experiment was surprising, and no, we don't think it's correct. Okay, so it's up to now someone else, because Tim is not working on this problem anymore. This is an advantage you have in India. In the US, we are very focused by who is funding us. And if we lose funding for a problem, then we really can't work on that problem anymore. So we have less flexibility to do things that, for example, take a decade to do. It's very hard to do that in the US because you would need to get a grant funded twice. And they don't like renewing things. They want each grant to be transformative and new. So so he doesn't work on it. But if you are interested in testing this prediction, that would be fantastic. It's a cloud point measurement. The materials are all commercially available, and experiments are always hard, right? And you guys are mostly theorists anyway. So and so we don't see this big difference that they saw in the experiment, and we have a physical reason for it. So what the physics that we have is that that this phase transition, it's phase separated at high temperatures, okay? Because these two, the energy difference is too high. But then as you decrease the temperature, it mixes. Why does it mix? And our physics for that is that there's a specific interaction between the cation and the polymer that allows this polymer to wrap around the cation. And so this specific interaction or attraction causes the polymer to mix with the cation. And the reason it occurs as high polymer concentrations is because a single molecule has to wrap around just a small number of cations. Okay? So it's not like you have many cations interacting with a single polymer. But if you put a methyl group right at that point here, it still wraps around the cation. It just does so in a different way. Okay, so what he had hoped to do in his experiment was say, yes, I think there is this interaction, and that's what's causing it to mix. And maybe if I put this methyl group, it will prevent that interaction, which it does, and that will cause it to phase separate. But what we argue is that it doesn't cause it to phase separate because this polymer still wraps around these other two, which are also negatively charged, partially, sites on this cation. So that's our physics. So we have a physics behind, we have not just the measurement, we have the simulations, we can look at all the configurations, and that's the physics that we think is causing this to happen. Okay, so that's with the supervised methods. I talked about neural nets. I won't talk about that too much anymore. But there's a whole other kind of machine learning, which is unsupervised methods. And so principal component analysis is the most popular one of those. And one of the things that goes into this, I'll talk about it briefly, is the choice of the feature vector from your system. Okay, so I'm actually much more enamored with these methods now than with the supervised methods, because you don't have to train anything. You don't even have to know if there is a phase transition. The method is supposed to tell you if there's a phase transition. Okay, so let me just briefly mention this. Support vector machines is also a classification method. So if you have two known classes, you find this hyperplane. Of course, here it's in 2D with just two components. But in principle, if you have a n molecule system, you have 3n coordinates. So you have to find some way of classifying these two, and then you find this hyperplane that divides these two, and then if you're evaluating it, you just find out whether it's on one side of the hyperplane or the other. Okay, so you have two known classes and this hyperplane, which is the support vector that classifies or separates them. Okay, so that's another supervised method. It's very popular in AI. Principal component analysis, let's say you had some feature vector. For Ising systems, this would be the n spin states for m coordinations. For each row would be the values of the spins at one temperature, and then state, and then you would have m rows each for the different configurations. So if you had 100 configurations at 100 temperatures, you have 100 times 100 rows, and if you had 1,000 spins, you would have 1,000 columns. Okay, so that's your matrix. And the covariance matrix is XX transpose. Okay, so now I can see how this is getting really unphysical, right? In the sense that you're starting to lose what the physics is, because it's a very complicated thing. And then you calculate the eigenvectors, and then you project this matrix onto the eigenvectors to get the principal components at each temperature. Okay, so you go through this process, and what you get is the principal components at each temperature in this system. Okay, so we usually look for 10 principal components. We usually use only 2. Okay, so it's sort of like if you had an ellipse, the principal components are the axes of this ellipse. But if you had n spins, then you lose that sort of physical interpretation of what they are. So this is a very old idea. It's I think it was from Turing or that time, the 40s, that people had thought of this as a way of characterizing the important structural features of a system. But that huge matrix, finding the eigenvectors of that is a very new thing. It has only been possible, recently, and especially with the GPUs, this diagonalizing matrix is really fast. So it's only recently that people have been able to use this in an effective way. So here's the 2D Ising model. This is done by an undergraduate in collaboration with a high school student. So he looks at the support vector machine and neural net, trains it on the two extremes, and then these are all the configurations they looked at. And red is when the system said it was mixed, and blue is when the net said it was phase separated. If you look at the principal components, there are clustering. So here's one cluster, here's another cluster, here's a third cluster. We have an algorithm to determine if 2 points are in the same cluster. And especially if you use this t-stochastic neighboring embedding, you can separate these clusters really well. Okay, so there are clearly 3 clusters, and then the rest sort of, you know, we don't know what they belong to. But our algorithm says that that is one cluster, the green, and the blue is a separate cluster. And so we say that a cluster corresponds to a different phase. Okay, so whenever we have a new cluster, it's a new phase. And from that, we can predict the critical point. So the PCA with the TSNE predicts 2.26. This is the support vector machine. That's the neural net. We have uncertainties because every time we do this, for each configuration, we get a different answer, right? And for each simulation. And so when we average over all of them, we get uncertainties. But compared to the Onsager result, there's an exact solution of this problem due to Onsager. It's very accurate, and it's independent of system size. So, uh, we do get rather large uncertainties in some cases. It's mostly because for the larger systems, we have fewer simulations. Okay, we have fewer, it's harder to do the simulation, so we have fewer snapshots. But there is no system size dependence when we increase the system size. Okay, so it's a real mystery. So our system, uh, our simulation method with our machine learning is giving us uh, a critical point that is independent of system size. In uh, in statistical mechanics, we have theories for how it should scale with system size. So this is a big surprise. Off-lattice systems, we don't have spins. So if we just choose the distances between the spheres, that would be one way of doing. You could choose just the positions or the distances as your feature vector, and neither of them gives you anything interesting. Neither of them gives you a clustering that shows a phase transition. But if you choose this affinity parameter, where you choose a cutoff, and for each sphere, and if there are more reds, you give it a +1. If it's otherwise, it's a -1. So then you have n. So you want to call it spins, you can call them spins. And so this affinity-based method gives you a feature vector that is more accurate, it turns out. And so here's the PCA for the distance-based. You don't see any clustering, and with the affinity-based, you see a clear clustering, right? So this is a low temperature. This is the high temperature. This is the low. And you see that there's some point at which this is a very, very different behavior. And so we associate that with the critical point of the system. Okay, so, and then if you look at that standard deviation, which is the variance in that coordinate, you see there's a clear peak at some point. So here is for the Whittam-Rollinson, we predict a critical point of 0.76 in density. This is the result we got from our earlier simulations. And for a binary Lennon-Jones mixture, we predict a critical point of 1.43. And that is the result from Kurt Binder's simulations of the same system. Okay, so this PCA unsupervised method gives results that are very accurate compared to previous simulations. So let me conclude by saying there are many things we had to do, but we did have first principle models that are very accurate for very complex systems. So if you want to study complex fluids in a way, the problem with polymers is there's not much experimental data. In biophysics, the situation is better. There's a lot of experimental data, so you can fit your force fields to that data. But in polymers, there isn't. So maybe this is a way to do it, to use these first principles models. I have it in these quotations because the reviewer did not like the use of the words ab initio or first principles, because DFT is not ab initio. Okay, so that was his objection, and so we just went along with it rather than fight with these quantum guys. They can be pretty nasty. So but you need long equilibration times. Okay, so that's a problem. But then we did find that these machine learning methods can sort of help us out a lot in getting the phase behavior. There's no other game in town. This is the only way to do it for such complex fluids. So it's going to take some time before people trust this method. But I think eventually, if you think back, most of you were not born then, uh, but there was a time, before you were born, when people did not believe computer simulations. So when I started out, when I was doing computer simulations, people thought that this was some like new useless thing. I remember Michael Fisher said that it was a sad street of simulations because we didn't even know what system size we needed, right? And so Michael Fisher was a very famous guy, very anti-computer simulations. But now it's an accepted tool. And so I think machine learning in physical sciences is eventually going to reach the same point as simulations have reached today. They're going to be a valuable tool that people can use to study their systems, and there are going to be a lot of people misusing them, okay, and not just like they do with simulations, okay. But we did argue that this is not published yet, but that you do need some physical insight to use machine learning, because if your feature vector doesn't have the uh, the essence of what you're looking for or what could happen, then the algorithms are not going to give you anything meaningful. So it's not just a boilerplate thing. You still need to have some physical insight in using it. Let me just conclude by acknowledging Jesse McDaniel started off all the stuff with the ionic liquids. Changyun and Hyuntae were students in my group at the time. He's a real leader. He's now a professor at Georgia Tech. And without him, I don't think these guys would have done anything. He was like this, you know, he was doing my job basically, getting them to motivated. And Supreet, a student from IIT Delhi, who's a postdoc in my group, uh, worked with the machine learning stuff with Inhyuk, who's a graduate student in my group. Hyuntae started all the machine learning stuff, and Aditya, as an undergrad in my group, was, someday he's going to